Hello, everyone. Welcome. Thank you very much. Thank you, Yuheng, for the very nice introduction, and especially thanks to Zhang for putting together this wonderful workshop. It's really my honor to participate in this workshop as the most junior faculty in this stellar group. So today I'm going to talk about independent learning in stochastic games. We'll be talking about where strategic decision making meets reinforcement learning. So first, I would like to thank my fantastic collaborators, Mohammed and Noah, and a special thanks to my PhD and postdoc advisors, Tamel, Asu, and Kostis. So I started with some motivation and introduction of RL. Then I realized there are many talks in this workshop that already set up the stage for me. So I just decided to just leave this one sentence. So we know that RL has attracted increasing attention lately. So please I refer to like Daria and Ben's wonderful talks yesterday, and also Shaofeng's talk today to have more background and why reinforcement learning is getting more and more popular nowadays. I'm sure they have better motivation than what I can do. This is one of my favorite, or many people's favorite example of what do we mean by RL and how what RL is really trying to solve. So RL is trying to solve the case where there is an autonomous agent trying to make sequential decisions in some unknown dynamic environment. So if you think about your agent as this self-driving car, and then the state would become your surrounding, the environment surrounding you, like the pedestrians or the position of other cars, as well as your own state, including your like your speed or your acceleration. And the action here correspond to the driving maneuvers. Either you will turn left, turn right, accelerate, or take a break. And the reward would correspond to like how fast you will reach your destination, and whether you are a good driver or not, whether you drive smoothly or not. You'll get different types of reward function. And by doing that, of course, sometimes like this is not exactly the same. Sometimes you may fall into the situation where you only have partial observation of the environment, all those stuff. But this is basically a typical paradigm. This feedback loop give you an illustration of what an RL agent is trying to solve. But what's really happening in this example is what's on the right-hand side, where each car is not driving on the road by its own. You have to take into consideration the interaction of multiple decision makers or multiple even RL agents. So what would happen in this case or is there anything interesting emerging here are the problems we are interested in. In fact, many more AI systems nowadays involve the interaction of multiple decision makers and multiple agents. Besides the example of self-driving car I mentioned here, like even in the very famous or the successful example of playing reinforcement learning, which is playing Go games, that by nature involves a two-player zero-sum game between two players. Another example includes like the control of unmanned vehicles, where there is a fleet or a team of agents that are trying to cooperate to achieve some goal as the navigation. They will, in some cases, they are allowed to communicate with each other. So this is by nature also a multi-agent control system. Some other examples include like the deployment of a fleet of robots in warehouse, or the cases where you have like human and robot interaction. Therefore, further advances critically depends on analyzing multi-agent interaction decisions and learning in dynamic environments. So then this brings us to the term of multi-agent RL. So I personally have worked on it during my PhD phase with some, I would say, pretty exciting results on the intersection of reinforcement learning and even H-infinity robust control. And also, if you notice, there has been a fast-growing line of recent advances on this topic, which has attracted huge attention from computer science, economics, and control. If you take a look at many of the workshops nowadays or programs at even ARO, Cyber Institute, NeurIPS, ACLEAR, or even CDC, they're just a lot over these years. Usually, multi-agent RL is studied under the general framework of Markov games or stochastic games. which originated from Shapley's seminal work back in '50s. So this is my favorite figure that really illustrates the relationship between the back comes forward. So the relationship between several like decision-making problems. So there are two axes, X and Y. The X corresponds to either you are making a one-shot static optimization or decision-making, or you are trying to solve a sequential decision-making or dynamic decision-making problem. On the Y-axis, that corresponds to the case where they're involved just one single decision maker, or there may be the interaction of multiple strategic decision makers. So in the first block, that will just correspond to the like optimization problem. We're trying to a static optimization problem that we solve. And this block, if you have multiple strategic decision makers, but you only care about one shot static objective, that will by nature give us the classical formulation of normal form games. On the other hand, if you have one single decision maker, but you care about some sequential like decision making, then that give us the the standard formulation of Markov decision process, and that's what the reinforcement learning, most reinforcement learning was trying to solve. So what we mean by multi-agent RL is trying to attack this stochastic game model, which is a strict generalization of MDP to this multi-agent decision-making problem. So however, I've been working on this for a while, and there are just many recent results on this. However, before we introduce our results, we were trying to think about why I mean, do we need to study multi-agent RL? Or even there is an intriguing question I've been thinking about for a while. So if multi-agent learning is the answer, what is really the question? I like that. So yeah, so it's been although I've worked on this problem for a while, but this intriguing question still confuses me for some time. So there are just so many recent results that are trying to either establish polynomial or even better sample and space complexity results, or even they consider the case where they assume the agents are adversarial. They're trying to establish some regret guarantees, or in game theoretic formulations or in game theory in general, equilibrium is usually a good solution concept people care about. So whether we should be caring about, we can have faster computation of the equilibrium and its computation complexity. Are those good or right questions to ask? Or even in general, Ben actually asked me this question yesterday. So does this really multi-agent perspective really provide new insight into decision making? More specifically, if you go back to the self-driving car example, so why can't we just model all the other agents that just as the surrounding, as part of the environment? I'm just trying to apply a single agent RL algorithm onto that. Whether there is some benefit by when you are taking this multi-agent perspective in your model. In other words, is standing equilibrium really all we need or all we have got today? In fact, equilibrium has been studied like for decades in game theory literature. So there's one traditional explanation of equilibrium, which is that equilibrium is something that results from the analysis and the introspection by the players, knowing the rules of the game, the rationality of the players, and payoff functions. Great examples include this, like textbook examples like Prison's Dilemma, Battle of Sexes, and many other examples. This perspective of viewing at equilibrium has motivated this whole literature of learning in games. Fudenberg and Levin, they even had a book on this topic back in the 90s. It's not a learning game, it's definitely not a new topic. In fact, they view this equilibrium arises as a long-run outcome of a process in which less than fully rational players grow for optimality over time. So agents are not necessarily like, fully rational. They may have bounded rationality. They're just trying to make their decisions, even myopic decisions, based on what they have seen so far. And equilibrium will sometimes or oftentimes just merge as the long-run outcome of this, naturally emerge at this decision-making of the collective behavior of multiple agents. This is one way to look at this equilibrium, instead of just looking at that as a solution concept we should be solving. Sorry, what? Yeah, replication is a great example of that. Yeah. But in general, like people view even Nash equilibrium, in general, like finite number of agents. In that case, they view like this kind of equilibrium as the emergent behavior of some, learning dynamics. But this kind of perspective has not been, well received by some of the learning, reinforcement, especially multi-agent reinforcement results lately, because they were more looking at this equilibrium as a solution concept, like the optimal of the optimization problem. But in fact, this is a slightly different but more interesting perspective that this, multi-agent learning can provide. So this perspective has been well established in normal form games. See, for example, Gutenberg. So what we were interested in was that, is this also true in stochastic games with state dynamics or even this RL setting? In fact, this infinite horizon, I will mention later why we emphasize this infinite horizon here. But in this infinite horizon stochastic game, the textbook setting with broad applications in economics, political science, and operations research. So if this is the case, that's great. But if not, in general, maybe it's just fine to embrace this learning dynamic. In other words, I learned lately from Christos he gave a talk at the Simons, which I feel like is very illuminating, is that maybe equilibrium is not something we should be looking for. Let's say the learning dynamics is very natural and very, very rational, but it never converges. There may be some oscillation. That's fine. We can just look at this learning dynamics as a solution concept instead of looking for equilibrium, or they call it let the dynamics show you the way. So this is more like on the game theory literature. On the other hand, in multi-agent RL, which is getting more and more popularity nowadays in machine learning and reinforcement learning specifically, so independent learning, which people call it, is used to describe the following setting, where each agent runs some variant of single agent RL algorithm to myopically improve her policy, and sometimes even oblivious to other agents or even the type of the game. Think about that self-driving car as an example. I don't care that much about what's really going on, what's really the decision made by other agents immediately. I just care about, I'm just maybe running some variant of a single agent RL independently. So technically, independent learning is known to suffer from convergence issues. There has been some earlier results that show some examples that if you just run, for example, individual Q-learning, even in two-player zero-sum stochastic games, it will not convert. The key issue here is something called non-stationarity issue, where if you really run this algorithm from one agent's perspective, because other agents are also adapting their policy, from your perspective, the environment is not a stationary macro decision process. So therefore, many conditions we need to prove convergence for single agent RL do not hold here. So this non-stationarity issue is really the challenge in this multi-agent, especially in this independent learning setting. But practically, independent learning seems to perform very well, at least better than I expected. There are some recent papers talking about whether this independent learning is all you need in the StarCraft multi-agent challenge, or the surprising effectiveness of PPO in cooperative multi-agent games, or independent algorithms can perform on par with multi-agent ones in cooperative and competitive settings. These are all pretty recent results. But I would say all of them are empirical results, empirical observations. This naturally raises the question of interest. So can equilibrium, or maybe more specifically Nash equilibrium for certain games, be realized by myopic and independent learning dynamics in this infinite horizon stochastic game? If so, in some cases, then it might in turn justify the success of independent learning in multi-agent RL in these certain cases. If not, in general, as we might expect, is there any possible fundamental reasons for that? So far, any questions? Yeah, that's a good question. So in this whole talk, we'll be talking about stochastic games, which is fully observable in the sense that the state is global and is observed by both players or even multiple players. But the action or the action taken by other players is unknown to me, or even I'm not even aware of the existence of other players. But the state is just globally observed. Yeah, yeah, I will be talking about the formal definitions. So, yeah. Any other questions? Cool. So this is a brief introduction of this model called stochastic games. Some people also call it Markov game. So we care about this infinite horizon discounted setting. So state is the state space. AI is the action space of player I, and each player has its own reward function Ri, which is affected by the joint action of everybody in this game. And in the special case of two-player zero-sum, where there are only two players, and also in the case where R1 plus R2 obviously equal to 0, this gives us a zero-sum, two-player zero-sum game. And also, like in MDP or RL, you have a transition dynamics P, and P here, the transition here depends on it's a Markov transition kernel. It depends on the previous state and the joint action of everybody. So also we have a discount factor that is smaller than 1. And one special case of this general framework is Go games, actually. So this special case in the sense that the transition, the state here corresponds to the position of the stones at each step. But in this case, this transition is something they call turn-based. Because every round, only one player gets to control the transition. That's a special case of the general framework. And in general, eventually you will get a reward after the game ends, because either one of them will win the game. It's also a zero-sum game, two-player zero-sum game. So now we talk about the solution concept, like Daria mentioned. We are looking at. So we are in this paper, in this talk, we will be looking at Markov stationary Nash equilibrium, which is exactly the same as the solution we are looking for in single agent RL, where we care about this policy class pi, where at each state, it gives us a mixed, possibly mixed distribution, mixed strategy over the action space. And we call this a strategy profile, which is a collection of everybody's policy. And then we can similarly define the expected value function for each player I, which is the long-term accumulated discounted reward starting from a specific state 0. But note that right now, although the reward function is only player I's reward function, but it's affected because the transition kernel here depends on, and also the reward here depends on the joint action of everybody. This value function would be a function of the joint policy or the strategy profile. Then what is the Markov stationary Nash equilibrium? It corresponds to a strategy profile pi star, which is a joint policy, such that at this point, at this pi star, nobody benefits from deviating from it. Okay? So at this point, if you fix the opponent strategy -i denotes the index for players other than player I. If you fix that policy, if you deviate from your pi star I, you will only lower your value. So this is what the solution we are looking for in this infinite horizon discounted game. And we know from literature that there always exists such a solution in infinite horizon discounted stochastic game, if you have finite state action spaces as the most basic model actually considered. And our results is that, our first result, I would say, is to show that independent learning made simple in the sense that we identify simple best response type dynamics with convergence guarantees to the Nash equilibrium in certain stochastic games. Specifically, learning dynamics requires no communication among agents, and it's symmetric, and is arguably what we argue is natural. I'll explain in a second. And also, each agent is unaware of the type of the game. For example, whether this is a zero-sum game or it's a cooperative game. It doesn't matter from this single agent perspective, and sometimes even unaware of the existence of other players. So the algorithm we call decentralized Q-learning. It's an independent learning algorithm without knowing the opponent. We consider a best response type learning dynamics, where the action or even the action set of the opponent cannot be observed. Specifically, to introduce the algorithm, we first introduce this notion of local Q function. As we can imagine, like if you define this Q function for player I, it will also be a joint. It will also be a function of a joint policy path. More importantly, the action here would correspond to a joint action, AI and A minus I. A local Q function means that if you marginalize over the opponent's policy pi minus I, that will give you a function, Q function that is only dependent on the local action. This quantity will be very important in our algorithm. There are two main steps in our algorithm. So the first step is that the player I will infer the opponent's strategy because he or she cannot directly observe that by estimating the local Q function. More specifically, we'll propose some Q-learning type. It's not exactly Q-learning, but Q-learning type kind of update rule, which is updated this way. So V hat is some quantity I'm going to introduce soon, but Q hat is the estimate of your local Q function, where the action here is taken from some smooth best response given your local Q function. So the tau here is some temperature parameter, and the nu here corresponds to some perturbation function. This is also something in learning games literature, they call it like smooth best response or smooth fictitious play in this fictitious play literature. But basically, if you choose this nu I to be an entropy function, then this argmax will have a closed form solution, which gives you just softmax. So this is how we sample this action. And to get a better idea about what we really change in this algorithm, so this is a vanilla independent Q-learning. So what they do, the only difference here is that in this vanilla independent Q-learning, as if you don't care about other agents and running Q-learning, you just take you are doing some kind of bootstrapping. You are just taking max directly for your own like local Q estimate. But what we do is that we are not doing this using your own Q estimate, but using a different variable, which we introduce in the second step, where the player I also estimate this value function in a different time scale. By saying time scale, we mean that here you are updating Q using the step size alpha, but here we are updating the V in a different step size beta. And the relationship between the two I'll introduce in the next slide. So all the quantities, note that all the quantities in this algorithm are maintained locally without the coordination or communication among agents. So recall, this is the learning dynamics we just proposed. There are several features of this learning dynamics. First of all, is that it's natural for self-interested players because from his or her perspective, it's basically like solving a single agent problem. Although there are still some difference from the vanilla individual Q-learning, and it's symmetric among agents. Each agent just runs a copy of this algorithm. However, actually many existing provable multi-agent algorithms, they don't enjoy all the properties here. They care more about equilibrium computation. Another very important feature of this learning dynamics is this two-time scale step size choice, or two-time scale separation, in the sense that as time goes to infinity, the step size of doing the second step should be relatively negligible compared to the step size of doing the local Q update. So what's the intuition here? Intuition is that if your step size satisfy this two-time scale separation, then you can kind of think of the update of the first one as if the V here is stationary. It's not changing over time. Then this first update rule is just trying to solve some auxiliary normal form game with this new payout function as if you are fixing this way ahead over time. This is the first, what this first update. And then we update V hat I as if then two-time scale, the beauty of this two-time scale separation is that then if you analyze the slower time scale, like the second one, you can view it as if the first one has solved to the optimal solution or solved to the end. Then what does it mean? It means that for this fix we have already solved this matrix game or normal form game. And then we plug in the solution to the outer loop to the slower time scale. This actually corresponds to the stochastic approximation of minimax value iteration for example, two-player zero-sum game. And this was actually the first algorithm introduced by Shapley in his seminal paper, try to solve these stochastic games using value iteration. And this lower time scale is trying to mimic that with some up to some stochastic noise. So this is the intuition why it works. Actually, this time scale separation would be the key to the convergence proof. Ramos-Moron condition. Yes, those kind of updates. Yeah. Thank you. Any other questions? I hope I explained that intuition here. Sorry. Yes. So it came from a smooth fast response. So it's a stochastic policy here. You're talking about here. Yes, I have a local update. Oh, sorry, I have a local iterate, a local variable q hat I. That's what I know about the environment, including the effect of my opponent. And then what I do is a very myopic thing. I just take some kind of smooth fast response with respect to that. And I sample from this policy, get my action, and system evolves. And then this is a the subtle but important difference from like independent killer. Single agent. Yes, exactly. Yeah, we will show the results. A very good question. Not to my knowledge. Because I feel like in single agent, they don't have the motivation to separate the time step. It's more like I would call it V-learning. This is updating value function. Yeah, that's a very good point. Is that like intuition here? And this timescale separation, interestingly, we kind of motivated from even some literature in evolutionary game theory and behavior economics. They say that usually this decision maker or this like, rational decision makers choices are more dynamic than their preferences. For example, you have a list of restaurants you would like to go to, what a list of like your preferences. But the way you change your decision is faster than you change your list or change your preference about the restaurant. Why that's relevant? So you can view this like this payoff of this auxiliary game, which is V-hat, as something like your preference. It's updated slowly. And then you use this, your preference to update your policy here in a relatively faster time. We are making these choices. We are making this immediate response. That's something we connect to some of the literature in economics. Also in learning games literature, especially in normal form games, this setting where you only have payoff signal, payoff feedback, is called radically uncoupled dynamics. So to our knowledge, there were no like radically uncoupled dynamics for stochastic games. But for normal form games, matrix games, this is a well-defined or well-acknowledged concept. And we are trying to solve this setting. So what can we show here? We first can show actually we can show that for two-player zero-sum stochastic games, this decentralized Q-learning dynamics will converge to a Nash equilibrium with the boundary. In the sense that the value estimate, the V-hat I, will converge to the, because in zero-sum games, the value of the game is unique. They will converge to the value of this zero-sum. Also, if you average over time by using this, like because we are using a different step size, not necessarily 1 over k, if you take a look at this alpha weighted time average policy, it will converge to the Nash equilibrium strategy of this zero-sum game. And more interestingly, I would say that go back to Prashant's question. There's also something called rationality guarantees in this multi-agent learning literature. So actually, it's an early notion proposed by Bowley and Veloso. They said that a desirable multi-agent RL algorithm should not only be convergent, or it should not only be looking for equilibrium, but also has to be rational, which is defined in the following way. So the iterate of one player will converge to the opponent's best response if the opponent converges or is using a stationary policy. In other words, meaning that you can exploit the weaker opponent. Thus, it is because if the opponent is just not adapting, you should be able to make use of this fact to exploit that fact. And this will in turn motivate the agent to follow this dynamics in the very first place, because that's a rational dynamics for me to use that. What we can show is that this learning dynamics is rational in this sense. If the opponent's strategy is asymptotically a stationary strategy, then we can convert to the best response to that, which is kind of expected because following the intuition I just explained, the convergence coming from just value iteration. So I don't know how much time left. Yeah. Okay, I'll try to be. We start a little bit late. Okay, so how far can we go with this independent learning paradigm, which I feel very excited about? Actually, we have to mention something called fictitious play, and also some notion we call game agnostic convergence. What does it mean? So actually why people love this independent learning dynamics is that one desired property of independent learning is that it is game type agnostic. One example is this very first learning game algorithm called fictitious play. So I would like to go through with you a little bit about this very typical, very interesting idea. So basically, they only have one line of update called the belief update. Means that for each agent I, you will maintain a belief of your opponent. You will maintain some estimate of this belief pi hat minus I, which is nothing but the time average of the play of the opponent. You can observe the action. In this case, it's a slightly easier setting where you are allowed to observe the action taken by other players. Then you just take an empirical average of it. You maintain this belief. Okay? And then what you do is that every time you just take a best response using this, because in this case, usually you know this matrix game, you know this matrix. You view it as if the opponent is using this belief as a strategy. Then I take argument. What do we mean by game agnostic convergence? One beauty about this fictitious play is that the same update rule for the agent from one agent's perspective will converge for not only zero-sum two-player game, but also like identical interest multiplayer game and 2x2 non-zero-sum normal form game setup. From each agent perspective, you don't need to change your update rule. So they say a game has fictitious play property FPP if fictitious play converges to its equilibrium. So do we have something or do we know anything about stochastic game? Yes, if you also use this 2 time scale separation idea. So this is what we proposed of fictitious play for stochastic game. It looks very similar as before. This is the update of your belief. Where for generality, we are using step size here. This is the action is a play observed from the opponent. But we also maintain an estimate of the Q value function, which is updated slowly. And then you are taking this best response as if you know this Q in this matrix. But you are updating this Q in a slower fashion. Eventually, as you can imagine, the update rule will mimic the min-max Q value equation in the two-player zero-sum. And we show that this very same fictitious play dynamics converts to Nash equilibrium for both zero-sum, which is the competitive setting, and also n-player single controller identical interest games. Single controller is a bit tricky here, means that only one of the player gets to control the transition of the dynamics. But the same learning, same update. If you change this to smooth fictitious play, we managed to show that it will work for both like competitive two-player zero-sum case and the general identical interest, not only the single controller. So maybe the last piece of this talk. So we have cracked like kind of two-player zero-sum and which is a competitive case, and the n-player identical interest, which is the fully cooperative case. What about the cases beyond that? What about in the infinite horizon general sum game? less study has been conducted in this area. Actually, there was a very interesting paper back in 2005 saying that if you just do value iteration-based approaches, you cannot converge to the stationary equilibrium in general for general sum stochastic game. They give a very interesting counterexample there. And our decentralized Q-learning I mentioned before cannot either, because if you recall, the reason why it works is because we reduce to min-max value iteration. And we have this beautiful like contracting property. However, this gamma contracting property breaks in the general sum case. So why is that? Because if you do naively do value iteration in this general sum game, every iteration, when you do backward, you need to solve a matrix game. But the matrix game, the equilibrium may not be unique. Even the value may not be unique. There may be some equilibrium selection problem. Every time we do backward, this operator may not necessarily be gamma contracting. In fact, it's unclear how to construct a stationary equilibrium from non-stationary ones. If you think about really like single agent like RL, or even two-player zero-sum case, which I call easier cases, if you do backward induction, and if you run like the value iteration long enough, you can just take out the first, the equilibrium at the first step, and use that as a stationary policy all the time. That will give you approximately good stationary solution. But that's essentially because of this contracting problem. But right now, even if we run this like value iteration, it converges, but if we take out the first one, it's unknown whether that's a good stationary solution. So there are some evidence there showing that general sum can be hard, but is there a fundamental reason why infinite horizon general sum stochastic games are challenging? So there might be one. We recently showed that with Kostis and Noah, we showed that finding Markov stationary equilibrium, whether you are talking about Nash equilibrium or correlated or coarse correlated equilibrium, which I didn't get a chance to introduce in this talk, in general sum case, is PPAD hard. So PPAD here means that polynomial parity argument on directed graphs basically is some notion in complexity theory